There is an idea in physics that's so ambitious, it's been called the theory of everything. But it's also so controversial that some people call it a theory of nothing. Yeah, it's a big one. Today, we're going to dive into the absolutely beautiful and frankly mind-bending world of string theory. It suggests that everything, you, me, the stars, it all boils down to one breathtakingly simple ingredient.
So, what if our entire universe is really just a symphony, a cosmic song played on these impossibly microscopic strings? What if every particle, every force, everything we see around us isn't some tiny little dot, but a little vibrating filament of pure energy? Now, that is the core question of string theory. And look, if it's right, it changes absolutely everything.
Okay, but why? I mean, why would physicists even come up with something that sounds so out there? Well, to get that, we have to look at this huge, gaping crack that's been running right through the foundation of modern physics. You see, for almost 100 years now, science has been living in a house divided against itself.
So, on one side, you've got Einstein's general relativity. It's this beautiful, super elegant theory of the very, very big. It describes the graceful dance of planets, galaxies, the warping of space-time itself. Then, on the other side, you have quantum mechanics, the wild, bizarre, but incredibly precise theory of the very, very small. It's all about the chaotic world of particles and forces. So what's the problem? They completely contradict each other. Their math, their fundamental rules, they just do not work together. At all.
And that is one of the deepest mysteries in all of science, right? How can reality run on two completely different operating systems? It just doesn't make sense. And finding a single unified theory that fixes this, a theory of everything, well, that's pretty much the holy grail of modern physics. And this is exactly where string theory walks onto the stage. It comes in with this potential solution, a radical, beautiful, and totally mind-bending way to finally bridge that great divide. The starting point is, well, it's deceptively simple. It basically asks, what if we've been looking at the universe all wrong? What if the fundamental building blocks of reality aren't these little zero-dimensional dots, but are instead tiny one-dimensional loops or segments of, string? And right here, this is where the idea becomes truly profound, because if this is right, there's only one fundamental ingredient in the entire cosmos, the string. That means all the wildly different particles we see, electrons, photons, quarks, they aren't actually different things at all. They're just the same fundamental string, vibrating at different frequencies. It's incredible to think about. The best way to think about it is like a violin string, right? A single string can play a C note, it can play a G note, an F sharp. It's the exact same string, it's just vibrating differently. So string theory says our universe works the same way. One pattern of vibration looks like an electron to us. A different one looks like a photon. And this simple idea, this leads to the theory's single biggest triumphs. Because it turns out that one specific vibration of this string has the exact properties needed to be the graviton. That's the long sought-after quantum particle of gravity. And just like that, in one fell swoop, gravity isn't the odd one out anymore. It's just another note in the cosmic symphony. I mean, that's the magic of the theory. It doesn't just allow for gravity, its math requires it. So this incredible power to unify all the forces and all the particles, that's why string theory gets called a theory of everything. But, like with all great revolutionary ideas in physics, this elegance comes with a very strange price tag. It turns out that for the beautiful mathematics of string theory to actually work, to not just collapse into complete nonsense, it makes one absolutely stunning demand. Our universe can't just have the 3 dimensions of space and one of time that we all know and love. Nope, it needs 10. The theory requires 9 dimensions of space and 1 of time. So, if that's true, where on Earth are the other 6 spatial dimensions? Why can't we see them? Okay, here's the classic analogy. Imagine a garden hose. From really far away, it just looks like a one-dimensional line, right? But if you're a tiny ant walking on it, you know you can move in 2 directions. You can go along its length, and you can also go around its circumference. Well, string theory suggests the extra 6 dimensions are just like that tiny circumference. They're compactified, which is just a fancy way of saying they're curled up on themselves at a scale so unimaginably small that we just can't perceive them. But even with this bizarre, kind of cool idea of hidden dimensions, the theory's development was a really winding road. By the early 1990s, physicists hit a new problem.
they didn't have one string theory. They had five. Five different, totally consistent versions of the theory. So, which one was the right one?
So, right after all these initial breakthroughs, the whole field kind of fragmented. But then, in 1995, the physicist Edward Witten took the stage at this huge conference and proposed something extraordinary. He basically kicked off what we now call the second superstring revolution.
Witten basically suggested that those 5 competing theories, they weren't competitors at all. He said they were just different mathematical perspectives on a single, even deeper theory, one that lives in 11 dimensions, by the way. He called it M-theory. It was this stunning revelation, showing that all 5 theories were just different facets of one mysterious, unified whole.
So, okay, we have this beautiful, seemingly all-encompassing framework. It unifies physics, it explains particles, it even has these wild hidden dimensions. But decades later, the crucial question remains, is any of it actually true? Because despite all its promise, string theory faces some enormous challenges.
And here's the thing, there is zero, and I mean zero, direct experimental evidence for string theory. The strings themselves, they're thought to be trillions of times smaller than an atom, just hopelessly beyond our reach. The theory also predicts something called supersymmetry, this idea that every particle we know has a heavier, undiscovered partner particle. And after decades of searching at colliders like the LHC, we found none of them, nada. And then there's what might be the theory's biggest internal hurdle of all. And this is what's known as the landscape problem. You see, the precise shape of those 6 tiny, curled-up dimensions is what determines the fundamental laws of physics in our universe. But here's the catch. It turns out there isn't just one way to curl them up. There are a staggering number of possible ways to do it.
The theory allows for something like 10 to the power of 500 different stable configurations. Let me just say that again. 10 with 500 zeros after it. Each one of those corresponds to a different possible universe, with its own unique set of physical laws. In a theory that predicts everything, well, in a way, it predicts nothing at all. As the physicist and critic Peter Voigt puts it, this enormous landscape of possibilities makes it almost impossible to use the theory to make a unique, testable prediction about our specific universe. You can always find some corner of the landscape that happens to match what we observe, but that isn't predictive science. That's what you'd call postdiction. And this really frames the debate perfectly today. Is string theory a window into the ultimate nature of reality, a true theory of everything that we just don't have the tools to test yet? Or is it just an incredibly powerful and mathematically beautiful idea that in the end has nothing to do with our universe? For now, the symphony remains unfinished.